Yeah, so welcome back everybody. So I'm Florian Schreck from the University of Amsterdam. We have strontium quantum gas experiments, and I'm going to tell you about how to prepare ultracold quantum gases for precision measurement. And there was a tiny misunderstanding between Marco and me who would teach about what. So in the break, I extended my talk from 45 minutes to 1.5 hours using lots of lecture material which I had. So it's okay, it's not perfect, so there might be some slides a little bit, improvised. We will, and it's not quite exactly as I would have done it, but I think it will be good enough. And yeah, just ask me questions during the lecture. Okay, so our goal is to build the best possible clock in the world, yeah? And clocks need a frequency reference. For us, it's of course atomic transitions. Now, what should we use here to get the best precision? Obviously, it's nice to use a transition with a high frequency and a narrow width. So an optical transition with a millihertz line width. So we are going to build optical clocks. Furthermore, we want to read out the signal of these atoms with large signal to noise. So we will send a laser beam onto our atoms and we will see if the atoms get excited or not. So we will record how many atoms got excited, and we can determine this. The better, the more atoms we have. Okay, use many atoms. Okay, many atoms. I'll just take a solid piece. There are lots of atoms in here. This will not work, yeah, because the atoms in a solid, they influence each other very strongly, and we can't even find the clock line anymore, which means we should use a guess of independent atoms. However, we want still a lot of atoms, and the laser beams with which we can influence our atoms have a finite size. For example, optical dipole traps have a size of typically 100 micrometer. So we want a quite dense gas of atoms and still avoid these disturbances. So we will want to nicely separate these atoms one from the other. We want to keep them apart. Next, we want to observe these atoms for a long time, which of course means we must make them slow, and we want to avoid Doppler shifts, and there are tricks. I'm pretty sure Michael also will describe the Lambda regime during the optical clock session. So we want to tightly confine our atoms so that we can completely suppress the Doppler shift. Now if we look at these conditions here, I marked 2 in green. We want a dense gas of atoms, and we want to have these atoms cold. These are actually the same conditions as going to a quantum gas. Yeah? And then the conditions here marked in blue, keep atoms apart and tightly confine them. This is the same condition as for a very special type of quantum gas, namely a Mott insulator. So the goal of my lecture will be to show you how to prepare a Mott insulator and use it for clocks. I'm not going to talk much about clocks, but just how to build this nice sample of atoms for clock spectroscopy. By the way, it's very important that when we manipulate our atoms and create this Mott insulator, so that we do all of this without introducing new systematic effects, light shifts or so. Okay, by laser cooling, we need new cooling techniques, evaporative cooling, and how we make and detect such a gas, and then for clocks, why it's important to use fermions and how to make a Fermi gas, what's difficult there. And in the second part, I'll describe to you what a Mott insulator is and why it's useful for clocks. And finally, I have a brief discussion of a 3D optical lattice clock, which was recently made in Junji's group. Okay, so let's take a gas of atoms, say at room temperature. You can, these particles, they move around with hundreds of meters per second velocity, and yeah, they are classical. Now we want to cool them down, of course, and then the velocity of the atoms goes down which also means that you know the velocity better and better. It's very close to zero, essentially zero. Now think of Heisenberg's uncertainty relation. If you know the velocity of something very well, you don't know the position. Here we know the velocity better and better because it's closer and closer to zero. So we don't know the position of the atoms anymore. So we shouldn't think about them anymore as classical particles. We can't know position and velocity precisely at the same time, and we need to use a different mathematical language, wave functions, that describe everything we can know about the atoms, the probability distribution, where they are in the momentum. And the size of this wave function, the de Broglie wavelength, depends on the velocity of the atoms. The slower they are, the bigger it gets. So if we cool even more, then these wavelets describing individual atoms, they will start to overlap. And if we are working with identical bosons, these wavelets will synchronize with each other and they can form a Bose-Einstein condensator, macroscopically occupied matter wave. Okay? Now, when does this happen? We need to compare the de Broglie wavelengths to the average distance between the particles, and we typically do this in terms of the so-called phase space density. You see here it's defined as the density times the de Broglie wavelength to the power of 3, which is, the density is 1 over distance to the power of 3. So here you have de Broglie wavelengths divided by distance to the power of 3. So if this becomes comparable, then it condenses. Yeah? Bose-Einstein condensation happens when the phase space density exceeds 2.6 for homogeneous gas. Now, what do we need to do to get a Bose-Einstein condensate? Let's for a moment forget about clocks and just concentrate about trying to create a Bose-Einstein condensate, trying to fulfill this condition. Yeah? We can see here we should have a high density, and here the de Broglie wavelength is anti-proportional square root of temperature, so we have to have a low temperature. Okay, so if your task is to create the first BEC in the world and you don't know how it's done today, like put yourself 30 years back in your mind, what would be a way to do it? And perhaps you would take just a bottle filled with gas and then squeeze the hell out of the atoms to get the density really, really high. Yeah? Perhaps this could get you a BEC. Let's try this. I fill a bottle with a gas of lithium atoms and push them together. Now, the real ground state of lithium is not a gas at ambient temperatures. It's really a chunk of metal. And if you just squish a gas of lithium atoms, rather than Bose condensing, you get chemistry. Yeah? 3-body recombination. 3 atoms collide with each other. 2 of these 3 atoms form a molecule that releases a lot of molecular binding energy, and this energy needs to go somewhere. Luckily, we have a third collisional partner. It can take up, so the molecular binding energy is converted into kinetic energy, and the molecule and the third collisional partner rush off in opposite directions. They need to do so for momentum conservation. These atoms approach each other rather slowly. The kinetic energy released from the chemical reaction is enormous, so the momentum has, for momentum conservation reasons, they need to go off in opposite directions with high speed. And this means this process here can only happen if you have 3 particles colliding. Just 2 colliding doesn't do it because there's no way to fulfill energy and momentum conservation at the same time. Okay? And this gives us an interesting way out of this dilemma. You see, 3-body collisions, they scale with the density squared. They become worse and worse and worse the more you increase your density, because one atom has to encounter a second atom, that's 1 multiplier of density here, and then these 2 have to encounter yet another atom, that gives you density squared. Okay, that means to avoid this process, we shouldn't exaggerate with our density. High density is nice for BEC, but don't overdo it. And typically from experience we know that the densities for BEC is in the order of 10 to the 14 atoms per centimeter cubed. And actually that's not all that dense, yeah? The molecules of air in air here are 10 to the 19 centimeters cubed, 100,000 times denser. Good. So that gives us a limit here for the density. And now if I plug this density limit into these equations, I can calculate how cold I should be. And it turns out, dependence of the mass of the atom, we should be in the region between a microkelvin and 10 nanokelvin. And that's pretty damn cold. So you can't reach this with a cryostat or a normal fridge. We need very, very special fridges. And here is how our fridge looks like. It's a big vacuum chamber here with an oven emitting an atomic beam of strontium, and then we have here laser cooling beams slowing this beam down and capturing the atoms in our mod. Let's walk through the technical details of this machine. Let's first start here with our oven. It's simply a steel tube filled with strontium, and we heat it up to like 500 degrees Celsius or so. And at the end of the tube, we have just a typical, we attach a bundle of tiny little tubes pointing in the forwards direction. Okay, now, okay, we heat this up a lot, so we insulate it nicely. And if we heat up our element, we create an atomic vapor. Here for rubidium, for example, you see you get a dramatic increase in vapor pressure. If you crank up the temperature, for rubidium you operate in the 100 to 150 degrees Celsius range. So in the oven chamber you have 10 to the minus 3, 10 to the minus 4 millibars. For strontium you need 500 degrees Celsius or so. Good, and that produces then an atomic beam with a velocity distribution like so. So typical velocities here are on the order of like 500 meters per second or so, quite high. Yeah, we need to go down to millimeter per second velocity. So, here's the atomic beam streaming out of the oven and being illuminated by a resonant beam of light. Good. Here's a little trick. Right. I think I'll skip that one. The atoms coming out of the nozzle, they diverge a little bit, and you can either make your nozzle smaller in diameter to get rid of this divergence, but that really quenches your flux. You don't want that. The better trick is to add a little transversal cooling stage, just as Marco explained, from the side, so that the atoms, which are not too fast going out sideways, they are collimated and also fly forwards. Just a technical detail, it can increase the flux by a small factor. Let's skip over this. Here's again a zoom on our machine, oven, transversal cooling section here, and here a collimated atomic beam comes out. And now we need to slow this down so much that a magneto-optical trap can capture it. And we do this by a single counter-propagating laser beam in a Siemens slower. So how does this work? Oven, atomic beam, slowing laser. Here is our velocity distribution, and we adjust the frequency of this Siemens slower beam such that we just address the high velocity atoms here. And these atoms are then slowed down to a lower velocity. And that's then the end of the story if you don't do anything more. But we want to cool all these atoms down to like 20 meters per second velocity. So what do we do to achieve this? We exploit the Zeeman effect. Yeah? If you have a simple atom like strontium with a J equals 0 to J equals 1 transition, the J equals 1 state is split like this with 1.4 megahertz per Gauss. And we now use this transition, which can be tuned with a magnetic field. We employ magnetic field coils, which produce a big magnetic field at the beginning of the Siemens slower and a small one at the end. And we tune our laser beam such that here at the beginning, with the applied magnetic field, the laser is in resonance with the fast atoms. These atoms then get slowed down, and a little bit later, for the same magnetic field, the laser beam wouldn't be in resonance anymore. But while the atoms slow down, they are also propagating forwards to a location where we have now less magnetic field, so less Zeeman splitting. So here we have less Zeeman shift and less Doppler shift from the lower velocity. So the laser, the same laser, is again in resonance, and can slow down our atoms, and so on and so forth, till we reach the end of the Semans law, where we have a velocity of what we choose, 20 meters per second or something like this. And that's now slow enough to capture the atoms in the magneto-optical trap this Marco described. 6 laser beams, or here molasses, 6 laser beams from 6 directions. All laser beams are detuned a little bit too low in frequency. They are not addressing the atomic resonance, they are lower in frequency. So if an atom is moving against one of these laser beams, it will absorb photon. It will see this laser beam at a higher frequency, so now on resonance, and absorb photons from this laser beam and be slowed down. And that happens in which direction the atoms move, and we can cool down to this Doppler temperature, which was described before. Okay, and then we want to trap them. That is done, like Marco described, by adding a quadrupole magnetic field and polarizing these lasers. So here, just looking on axis, we have this situation. B field is on axis like this, and the magnetic field then shifts the states. And the atoms which are drifting towards the right, they can only absorb photons from the laser beam from the right and be pushed back and the other way around. Okay, so that was already described by Marco, and here we see the end result in our machine, the fluorescence of a tiny cloud of strontium atoms. Actually here it's a reflection of the magneto-optical trap actually is here. This is a reflection of the fluorescence in the window of our glass vacuum chamber. Good, and there was a Nobel Prize for this, Steve Chu, Contanucci, Bill Phillips. Now, in a mod we can't cool enough for BEC. First of all, there's of course a recoil limit. If you have even if you have a stationary atom, a photon hits the atom, it gives it a momentum of h bar k. And if you plug this in here, you see that there's a temperature under which we can't cool easily, the recoil limit. But it's even worse. There's also a Doppler cooling limit. That what Marco said this already. Theoretically, I have pictures describing this graphically. So here are these 2 laser beams. Here's the laser cooling force So if here's velocity. If the atom is moving in the positive direction, it will see this laser beam tuned to resonance, which will push it to the negative direction. So if a negative force here and the other way around. So this is the cooling force independence of velocity. And here in the middle, for really cold atoms, you see it's linear with velocity. Okay, and that gives you a damping force. But the damping is limited by this random walk, which we saw already. And I'll show this to you now graphically in 1D. Imagine we have a single beam pair which can push the atom up and down. And I start here in this numerical simulation with like 10 atoms or so at 0 velocity. And then they randomly absorb photons from these 2 cooling beams. And you see they just spread out with square root of t, just a Brownian motion, a random walk. Now, we do this diffusive motion together with this linear restoring force. And let's do the same simulation again here without the restoring force. It's just a momentum space diffusion. And this restoring force, the size is just limited here. And this is just the temperature, and Marco showed you how to derive this equation. What I want to point out here is that this here, for the best detuning, for the best cooling, is proportional to the line width of the optical transition that you are using for cooling. So that's very important. You can cool lower if you have a narrow line, and that's what we have in strontium. We have not only a 30 megahertz line, but also a kilohertz line. Good, and now let's see for time if I can describe Sisyphus cooling. I think I can briefly describe it. Now, as Mark, you said a little bit, but you didn't describe how it works. So now I'll describe it. So okay, now you mentioned already that people knew about this Doppler cooling process before making magneto-optical traps or molasses, yeah? And Bill Phillips constructed the sodium machine, and then they just looked for the temperature of the atoms in the molasses. So you have a little cloud of atoms, cooled down, and then they suddenly switch their laser beams off. This cloud of atoms will then drop in gravity, but the atoms will also continue to move in the random direction in which they moved at the moment when you switched your cooling lasers off. So this little cloud of atoms, while it's falling, will also expand. And then they had here a sheet of laser light through which this expanding cloud had fallen. Every time an atom crossed this sheet, it fluoresced, and they could detect that happens here on this detector. And then they got curves like so, yeah? So and the surprise discovery was from these curves you can extract how big this ball of atoms is, and therefore you can extract the temperature, yeah? If you're colder, obviously this doesn't expand as much as if you're hot. So from these curves they got now that the temperature of their cloud was 40 microkelvin only, whereas the Doppler limit, the prediction, is 240 microkelvin. So, and here's the graph which Marco showed again. This is the prediction of the simple Doppler theory. This is what they measured. Now, it's pretty usual that experimental data doesn't lie on predictions. But it's highly unusual that it's better than what was predicted. Yeah? Usually it's the other way around. So how does this come about? So let me try to explain this. First of all, sodium, or an alkali in general, is not a simple two-level system which was assumed, of course, for Doppler cooling. It's a multi-level atom. For example, we could have an atom with a spin 1/2 in the ground state, and then optically excited you have a J-quiz 3/2 state. This is just the simplest possible scenario to explain the Sisyphus cooling effect, so that's why I chose it. Now, you have to know that these various transitions between the ground state manifold and the excited state manifold, they have different line strengths, described to you by Clebsch-Gordon coefficients squared. You might have heard of this before, I don't know. Okay, for example, here if you have sigma plus polarized light, you get a very strong transition here, but a much weaker one here. Okay, this is the first ingredient which we need. You have to keep this in mind. So the second ingredient is that the laser beams which they used for their optical molasses, they were sigma polarized. And actually that creates a very interesting pattern of polarizations in space. Yeah? I mean, if you had just linearly polarized light and linear in the same direction, the standing you get a standing wave because you have the same frequency, and it would be very simple. It would just be electric field going up and down, and that's it. Here, if you have, for example, either you come in with sigma polarized lights from the side, or you can also say you come in with linearly polarized light with orthogonal directions, then at each point in space you get an interference between these two laser beams, making your electric field like rotate in one direction or rotate at a different location in the other direction. Yes, you can walk through this later. Yeah, let's just believe me that it's like this. Okay. Now, the last ingredient which you need to know about are these light shifts. Marco, you mentioned them somewhat, yes? So you called it the reactive force. What was it that? Yes. Okay, so if we have laser light that is not quite resonant with an atomic transition, and that's the case here. My molasses lasers are detuned. They are too low in frequency relative to the optical transition. Then I will shift the energy of the states that you couple. And now this gives, let's walk through this slowly. Here's my my term scheme with the various transition strengths here. Blue are transitions which are driven by sigma plus light, where the electric field is rotating in one direction. Red are the transitions with sigma minus light, where the electric field is rotating in the other transition. I told you from the interference of these two molasses laser beams, I do have spatial regions in which I have only sigma minus and others in which I have sigma plus light. Yeah? Okay. Now, this does something with the lower states here. This shifts these two lower states around in energy. Where I do have a lot of this sigma plus light, for example, the G plus 1/2 state is shifted downwards in energy. I'll explain this in the context of dipole traps a little bit better in case you don't know, just believe me at this moment. And where we have sigma minus light, the G minus 1/2 state is influenced the most and pushed downwards. So you see now you have this lattice pattern of energy of your two ground states of these atoms, okay? Now what does this do to the motion of the atoms? Oh, yeah, wait, okay. There's one last tiny ingredient and then we are done with all the ingredients. Yeah? The last ingredient which we need to know about is optical pumping. So if I have an atom in the G minus 1/2 state, for example, and there's only sigma plus light present, and then it can absorb a photon and by spontaneous emission fall back or go to the G plus 1/2 state. If it's in the G plus 1/2 state, it can again absorb a photon, but from this state, it can only go to the plus 1/2 state, not to the minus 1/2 state. Which means sigma plus light is always going to pump your atoms into the G plus 1/2 state and the other way around. And also sigma plus light addresses the G plus 1/2 state more than the G minus 1/2 state. Okay, now in the other way around here. Now let's put everything together. Here is this potential landscape that the atoms are seeing. So let's assume our atom is initially in this G plus 1/2 state, yes? And we assume it moves to the right. Yeah. Because it's in the G plus 1/2 state, there's a strong and here we have a lot of G plus sigma plus light, we have a strong light shift, so there is this hill. So the atom travels up this hill, which of course means that kinetic energy is converted into potential energy. Now up here on this hill, actually, we see that the G minus 1/2 state is shifted the most, so we must have a lot of sigma minus light at this location. And sigma minus light pumps atoms from the G plus 1/2 state into the G minus 1/2 state. You remember? So from here, what will very soon happen is that the photon will be absorbed and the atom will then be optically pumped. Now this is wrong, this should be plus 1/2 here. And it has a decent chance of decaying down to the minus 1/2 state. Yeah? And then the atom moves up the hill again. At that location, we have a lot of sigma plus light again, so it's pumped into the opposite direction and it moves up. Look what happened to the atom, huh? It's much slower now. So this whole process here slowed the atoms down. And the people who recognized this first, it reminded them of Greek mythology. Yeah? I mean, it was mentioned a few times already. This thing here is Sisyphus cooling. Okay. Good, and it works nicely if you do have alkalis with large hyperfine splitting, rubidium or something like this. Yeah, it doesn't work as nicely or as naturally for strontium. Oh yeah, okay, good, the cooling force. But yes?
Can I have a tricky question?
Sure.
Because you know, Florian, I never saw a magneto-optical trap made with linear polarized beam.
Right.
So on the other, all are made of circular polarization beam, which are not making this picture because they don't make this sigma plus linear, sigma minus linear letter. And on the other hand, in most of the trap, I saw subdoppler cooling.
Yeah. Sure, it doesn't make a polarization pattern.
No,
I mean, there must be some kind of polarization pattern.
Linear polarization
Which rotates.
is
Okay, then the picture is more complicated, I guess. Yeah. I didn't walk through that more complicated case. Did you?
Yes. It's a so-called polarization gradient cooling that you can transverse to this picture, but the point is that the atoms are not going through different intensity and different light shapes. They rather change the quantization axis, and then is a complicated quantum mechanics that can give you the same picture and gives you the same. Actually, what is giving you is this picture with this small bump that you showed us before. And in fact, the Sisyphus cooling in the simple form probably was used something like once or twice in our history as a scientist. So it's never used. There's always two sigma minus, sigma minus, sigma plus beams. But that's something that you have to actually read in the article and try to understand this whole picture because it's very complicated. It's not so easy as one guy in the stone.
Okay. Good. And yeah, for strontium is also not so easy because you have to artificially produce Sisyphus cooling. So we did this last year. So we had here a beam of strontium atoms traveling through an optical dipole guide. And then in this region over here, we slowed the atoms down by Sisyphus cooling. So yeah, perhaps it's a bit too advanced for some, but yeah. How did we do this? So the lattice we got by shifting the optically excited state of the narrow line cooling transition of strontium up and down. Yeah, we just used an AC Stark shift between 3p1 and 3s1 here, making a sinusoidal lattice. And then when the atoms arrive here with a velocity of perhaps 10 centimeter per second or so, we excite them on the kilohertz line with cooling transition, but only when they are at the bottom of one of these lattice potentials. Yeah, we can do this because the modulation here is much deeper than 7 kilohertz. And if an atom is excited to the state it lives there for a long time, 22 microseconds, there's plenty of time to climb up the hill. At some point it will spontaneously emit a photon and fall down again, but it has lost an average half of the full height of the lattice. So it's a very efficient cooling mechanism. Yeah, it allows you to cool with very little photons and in unusual situations. Manuel Endres' group showed also that this is very useful to cool strontium atoms in tweezers. Okay, here you see if you switch the decelerator on, atoms accumulate at this location. Good, and yeah, recoil cooling is a limit here. Okay, so that was laser cooling of atoms towards BEC. How can we reach these low temperatures? And we saw that there are strict limits to how cold we can get. In addition, there are strict limits on how dense you can get, because if you have a dense cloud of atoms which is laser cooled, one atom might absorb a photon from a laser cooling beam and scatter it. And this scattered photon doesn't just disappear afterwards. There's a decent probability that this photon is absorbed by some neighboring atom in the cloud and scattered again. And this gives rise effectively to a repulsive force between the atoms in the cloud. So you do have a limit on the density as well. So it's not so easy to reach Bose-Einstein condensation under these conditions. So we figured out a trick how you can reach BEC by laser cooling alone still, but I'm more describing to how people usually do it. And yeah, first, if you see this, you are sad. The photons, which are so nice to cool our atoms to yeah, meters per second or so velocity, now they heat the slowest atoms and push them apart. And that means now, yeah, we have to change strategy. We have to somehow trap them differently, not in a mod. And we need to cool them without near resonant light. Okay, so, oops, just made the slide. So, to trap them, we can use either magnetic traps or, for non-magnetic atoms in which this doesn't work, optical dipole traps. And for cooling, we will use evaporative cooling. Okay, so let's just look at a magnetic trap here. So alkali atoms, they have one Bohr magneton magnetic moment, and their ground state then splits up like so in a magnetic field. And some of these states here, they like being in low magnetic fields. They are called the low field seekers. And they can be trapped in a minimum of the magnetic field. And then we have high field seekers. And yeah, in principle, you could trap them in a B field maximum, but Maxwell's equations don't allow you to create that. So we can't trap them. And if we build a trap that traps the low field seekers, one that has a minimum in the center and grows in all directions, it will actually expel high field seekers. Okay, now we can use this to perform evaporative cooling. If we had a cloud of atoms trapped in a magnetic trap, we can just couple this trapped state using radio frequency to an untrapped state, and then they evaporate. Yeah, so we can very selectively evaporate atoms that at a certain spatial location, and if the atoms, they are oscillating around in a potential here, the ones which reach this location have the most energy, so we can evaporate the hottest atoms. So how to build a magnetic trap? The simplest is just a quadrupole magnetic field. It has 0 in the center and grows in all directions like so. The magnetic trapping is only interested in the absolute value of the magnetic field, so yes, you get a trap. And for rubidium to overcome gravity, you need like 15 Gauss per centimeter, and typically you use more like 100 Gauss per centimeter. Good. Yeah, what did I want to say? I think what this is an interesting story, perhaps. So, okay, yeah, good. I'll show you the whole story. So, to perform evaporative cooling, we need to keep our atoms around for a long time, yeah. And there are many effects which could eject atoms from our magnetic trap. First of all, of course, if your vacuum is bad, the residual, like hydrogen molecules, can crash into one of these trapped atoms and kick them out. So we need very good vacuum to create Bose-Einstein condensates. Second, three-body recombination. 3 atoms can get close to each other to form a molecule. You need the third for momentum conservation, just as described before. So we need to keep the gas density low. The residual near resonant light, if you scatter a photon off of this atom, it can perform optical pumping and bring you in an untrapped state. This is very dangerous. So you really have to make sure that all these laser beams you used for the magneto-optical trap and the Siemens law and so, they're really shuttered off if you perform evaporative cooling in a magnetic trap. Heating and loss by trap shaking, use stable magnetic fields, spin relaxation and Majorana flips. So say if you had 2 atoms in this spin state, they could collide. Angular momentum would allow you for one atom to go here and another here, and this atom is then not trapped anymore. Yeah. So we need to use these stretched states here, I mean this here or that state. They are stable against spin relaxation. And then there's also a danger specific to quadrupole magnetic traps, which is called Majorana spin flip. So here are the magnetic field lines which this quadrupole magnetic trap makes. You can also make them with permanent magnets if you want. And your atom is a little permanent magnet itself, yeah? And it moves around in this magnetic field, yeah? And you can imagine it precesses around these magnetic field lines. And if this precession frequency here is very fast with respect to the frequency, say the change in the orientation of the magnetic field line, to which you can also associate a frequency, yeah, how long would it take for a full rotation. So if the precession of the magnet of the atom around the field line is much faster than the change in orientation of the field line, then the atom will just follow, the atomic spin will just follow the orientation of the field line, and you will always stay trapped. I mean, you will always stay in the same stretched state. Okay, so there's this condition to be fulfilled. The Larmor frequency, here, the rotation of the spin around the field line, must be much faster than the rate of change of the B field direction. And this Larmor frequency is just the famous 1.4 megahertz per Gauss. It's per Gauss. So if your magnetic field is small, then the Larmor precession is small. And look, this is a quadrupole magnetic field. In the middle of the trap, it's truly zero. So you don't have any Larmor precession anymore. Which means if you have an atom which flies through the center here, let's say it comes in spin-oriented like this, it doesn't get guided and flips its spin. It flies through and keeps its spin in the same direction, which is terrible. Yeah, it's like a bar magnet, and instead of being repulsed or so from your magnet, you flip it around and it does the wrong thing. So this atom, an atom which flies by near the center, will just end up in the wrong spin state and be lost. So we need to avoid regions of low fields, and there are lots of tricks how to do this. Yeah, one trick is the so-called Pritchard trap. You use only a 2D quadrupole magnetic field. So then you have a whole line in the center where you do have the Majorana spin flip problem, but you plug this by using so-called pinch coils here at the end. These coils here create a magnetic field along this axis. So there is no point in space anymore where you have no magnetic field. In addition, you can use this axial magnetic field by the pinch coils to give you an additional trapping potential in this direction. Yeah, the quadrupole traps you sideways and the pinch coils trap you axially. Okay, that's a Pritchard trap. This is one I built during my PhD. The yellow-green thing here. This is how it looks in reality. Lots of water-cooled coils. Good. Now, this is all fine and nice for alkali elements who have a magnetic moment, but we are, of course, more interested working with strontium. And strontium, as you might know, is non-magnetic. Look at the term scheme. We have two valence electrons. In the ground state here, 1 is 0. We have a singlet state, yeah? No magnetic moment anymore. So magnetic traps, are, at least in the ground state of strontium, are not usable. And therefore, we need to build a trap for non-magnetic atoms. We use the electric field to trap the atom. Here's an atom, electron shell, nucleus. I apply an electric field. It polarizes the atom. And this induced dipole then experiences an energy shift in the externally applied electric field. Okay? So the energy of this atom is lowered. Great. And then you think, yeah, I'll just need to shape my electric field such that I have a maximum in the center and it gets weaker outside. Now, we don't do this with static electric fields. We do this with alternating electric fields. Here's a laser beam. It's not a near-resonant laser beam. So the atom barely absorbs photon from this laser beam. It's an infrared laser beam. And since it's infrared, the frequency of this laser beam is way slower than the timescale on which the electron shell can react on the electric field. Yeah? So the electron shell is always shifted to the side such that you have an electric dipole parallel to the electric field. So the energy of the atom is lowered if you have this infrared laser beam there. And now to build a trap, you just need to make a region in space where you have a lot of this infrared light. Now in the simplest case, you just focus a Gaussian laser beam and bam, it traps your atoms at the intensity maximum. And that's great. It works beautifully for strontium. So now let's go back to our machine, our strontium machine, and back to making a Bose-Einstein condensate. So we learned how to make a mod at this place here. And initially, as I said, the atoms coming out of the oven have a velocity of 500 meters per second. This is really damn fast. You need to scatter, I mean, every photon scattered takes away perhaps half a centimeter per second velocity. Starting 500 meters per second, you need tenths of thousands of photons. And the time it takes an atom to fly through the machine from the oven to the mod, yeah, it's just a few 10 milliseconds, which means you need to scatter tens of thousands of photons in a few 10 milliseconds. That means you need to use a very strong transition. For example, this transition here in strontium, which has a line width of 30 megahertz. That can do it. And we can, of course, make a nice mod on this blue transition. However, as Marco already said, the mod is super hot. Millikelvin. It's really poor performance for mods compared to, say, alkalis. However, in strontium, we also have these nice intercombination lines here, yeah? From singlet to triplet. It's really hard for an electric field to flip the spin of an electron. You would have to couple to the magnetic moment of the electron. And this transition actually is only allowed because you have spin-orbit coupling in your atom, mixing the 1p1 state with the 3p1 state. So actually, it's an electric dipole transition, but it's driving from this state to the contribution of 1p1 mixed by spin orbit into 3p1. Okay? And this gives rise to this nice 7.4 kilohertz line width transition. And yes, we know that the Doppler temperature is proportional to the line width. So you see, we go a factor 1,000 down in line width, you go a factor 1,000 down in temperature. That's great. And the phase space density goes up quite a bit here in our mod to 10 to the minus 3. And actually, you can laser cool even better. The reason why you only, so to say, go to 10 to the minus 3, which is still good, alkalis go to 10 to the minus 5 or so at this stage, is because these mod beams are relatively intense, because you need to levitate your atoms against gravity. And that yeah, needs a certain intensity in your laser beams here. Now, if we load our atoms into an optical dipole trap, this problem is gone. They are levitated from alone. And we are allowed to reduce the power in our laser cooling beams. And that then makes laser cooling much more efficient, and we can go to a phase space density of 0.1, bam, just like that. Yeah, alkalis don't do that. By the way, having a magneto-optical trap with just 1 microkelvin temperature is really nice, because that means the optical dipole traps you are using don't need to be deep. 10 microkelvin is a plenty. Another thing, by the way, you see is that the blue mod is very big and round and so on. Yeah, it's very hot. The red mod is cold, and gravity plays a big role. The atoms are sucked down by gravity. You see, they occupy only the lower part, kind of that's the resonance condition between the magnetic field and the vertically upwards rising laser beam. So your cloud looks like a pancake. So we typically also shape our optical dipole traps like pancakes to capture many, many atoms. Okay, now we perform evaporative cooling. So yeah. So we have our cloud of atoms in the dipole trap. It has a finite trap steps, and the hottest atoms evaporate. The remaining ones perform elastic collisions and rethermalize at a lower temperature, of course. Now, if we keep our trap high, that means we have less and less atoms that could evaporate, and the process would slow down and not work anymore. So people pull the depths of their dipole potential down just by reducing the laser power. That takes between half a second to 10 seconds or so, in dependence of how many atoms you have, what you want. And then, if you're just cold enough, the atoms condense. And how do we see that we have a Bose-Einstein condensate? Yeah, absorption imaging. We send a resonant laser beam through our atoms and have an imaging system taking a picture here. That looks pretty ugly, doesn't it? This is because you can never ever have a clean beam. There are always like fringes in your laser beam. So to get a nicer image, we just take a second image without atoms, and then we normalize these two images with each other, and we take the logarithm to get the density, and then we plot them fancily in 3D to impress people. And this is the shape of a Bose-Einstein condensate. Now, you ask me, how do I know this is a BEC? Could be also a thermal cloud, no? Yeah, we need to now carefully analyze these density profiles. Let's just first, for simplicity, look at how a thermal gas looks like in these images. And I'm not just, here's my dipole trap, here's my thermal gas. Now, for these images, I will switch the trap off, and the atoms fall in gravity and they expand sideways because they have temperature. And then I take an image and it looks like a round blob, yeah? A Gaussian distribution. And from the widths here, I can read off the temperature of the cloud. And from the integral, I can calculate the total atom number. Now let's do the same thing with a Bose-Einstein condensate. And that will behave very differently. So if I let a BEC expand, it looks at the end like this here. Now, why is this? This looks absolutely not round anymore at all. Why is this? So, in a BEC, the atoms interact with each other. Yeah? They repulse each other typically. So, okay, let's forget about this image. Just listen to me. So we have this gas cloud, and the atoms are repulsing each other in this dipole trap, yeah? And this trap confines the atoms very strongly in the vertical direction because we do need to levitate the atoms against gravity. There's no way around this. Whereas in the horizontal plane, we typically don't trap our atoms as strongly because we want to have a lot of atoms for a given density, so we make our system big in the horizontal plane. So our BEC at the beginning in the trap looks like a pancake. And it has this mean field interaction energy between the atoms. Now when I release, also perhaps I should make a picture. I have this picture here. You can also show that this mean field repulsion influences the wave function, how it looks like in the trap. And you can show with the Gross-Pitagorski equation very easily that the shape of the BEC in the trap is the mirror image, minus the trapping potential. So if you have a harmonic trap, it looks like a parabola. Okay, now this is a stable situation with trap. Now we suddenly switch the trap off. So you now have this gas cloud with a lot of mean field repulsion stored in it with this shape. Now imagine you have an atom sitting here. It sees this shape here because of the mean field repulsion is a potential which your atom sees. So it's an atom here at the side is sitting on the edge of a hill and it rolls down this potential and accelerates, yes? Okay. Now in the vertical direction, this cloud is quite small, yeah, pancake, small, whereas in the horizontal plane it's really big, which means the slope here of this mean field potential hill is very steep in the vertical direction, whereas in the horizontal direction you barely have any slope. And that means the atoms are dramatically accelerated vertically up and down, but not laterally. Yeah? And that leads to this expansion. We have the pancake falling and then looking like an vertical ellipsoid, like a cigar seen from the side. And I can observe this expansion even in time of flight. This is an in situ image in the trap. Okay, our resolution of the imaging system isn't good enough to show you the real tiny height of the pancake, but yeah, you see the ellipticity is definitely different than after the expansion. So this is one big signature of Bose-Einstein condensate, one of the smoking guns. The other smoking gun is that if you start with a thermal gas, not all atoms will condense at once. If you cross the phase transition, there will be both thermal atoms and atoms in the BEC, which have this very different type of expansion behavior. And you can see it here if you make a cross section. You see a Gaussian thermal background and a little BEC on top of it. Yeah, so this bimodal distribution when crossing the phase transition is the second smoking gun we have. Good. And that's just to look nice. Thermal gas, BEC, pure BEC, barely any thermal atoms anymore. And we can make strontium-84 BECs with up to 10 million atoms. Good, and the first BECs were done with rubidium and sodium at Chile and MIT, and of course that also gave rise to a Nobel Prize.
What's the temperature of the oven for getting 10 million?
Also 500 degrees. The air doesn't, 550 perhaps. It's really more about the shape of your optical dipole trap. It must be huge in the horizontal plane, and about the quality of your vacuum. We need to accumulate lots and lots of atoms in what we call the metastable reservoir, the 3p2 state. I didn't explain that trick. Yeah. Okay. Now, other questions on this part?
So you said 10 million atoms, 10 to 7?
Yeah, we can have that. But typically we don't bother. We can do our science often with just 10 to the 5 atoms very well. But if we really wanted to, we can push it up to that, yes.
So then we have evaporation times of the order of, say,
yeah, that experiment. Oh yeah, so in the okay. We have a poster on these issues, on how to create great sources. So we have one source, which is this atomic beam I described, which has a 1 microkelvin, and that's 30 million atoms per second, yeah. Condensate here with the 10 million, that was a cycle time of nearly a minute, so yeah. Good. Now, we want to build a clock, yeah? And in strontium, we have a beautiful clock transition. It's between two non-magnetic states, which of course it's important that clock transitions are non-magnetic. Between 1 is 0 and 3p 0. Now, in bosonic strontium, this transition is forbidden if you don't do anything like applying a magnetic field or so. Yeah, an electric dipole transition just can't do it. There's in fermionic strontium, you do have a nuclear spin, and this nuclear spin gives rise to hyperfine structure, and it mixes all these 3p states with each other, especially the 3p1 state and the 3p0 state are tiny little bit mixed. And that allows you, as an electric dipole transition, to drive 1s0 to 3p0 with a line width of 1 millihertz. And that's nice to have. It simplifies clock construction. So far, everything I told you was cooling both gases to quantum degeneracy, making BECs. Now, for fermions, that's slightly different. First of all, we have this hyperfine. Perhaps you want to know why these are bosons. I mean, just count. We have it's a 2 electron atom, so if you have even number of electrons, so an even number of protons. So protons and electrons together don't matter for the spin. Then here in the even ones, you have an even number of neutrons. So in total, you have an even number of spin 1.5 particles adding up. So definitely the spin, total spin here is going to be even, so you have bosons up here. And the nuclear spin is because you have an even nucleus, they are always spin 0. And here in fermionic, you have an odd number of neutrons in the nucleus bumped. So you have an odd number of spin 1.5 particles adding up to a total spin 1.5, which is 9 halves, and then you have a fermion. So, and this nuclear spin makes a complication. It creates hyperfine structure in 3p1. So the simple, for the blue line cooling, the broad line, it doesn't matter, but for the red cooling, that gives rise to some complication, dark states, and so on. We mentioned this already twice. We can slightly modify this red laser cooling by adding a steering beam to avoid the dark states, or use swap cooling. And then during evaporative cooling, we also have a complication. Identical fermions just don't collide in S-wave at ultra-cold temperatures. And we need elastic collisions for the thermalization during the evaporative cooling process. So evaporation just doesn't work with identical fermions. And here the solution is to prepare a mixture of atoms in at least 2 different of the ground state nuclear spin states. Yeah, say minus 9.5 and plus 9.5, and I have 2 different distinguishable fermions, and distinguishable particles can always collide. So yeah, I think I have time to explain why identical fermions don't collide in S-wave. So here just are 2 atoms colliding with each other. Here B is the collisional parameter, mass, velocity, and the angular momentum L is of course mvb here. And this is quantized, quantum mechanics. So we can have here angular momentum zeros and S-wave collision, P, D, and so on. And this determines the symmetry of the collision. And now you know, of course, that the wave functions of bosons or fermions have to obey some symmetry rule. So bosons are only allowed to collide in S and D wave and so on, whereas fermions are only allowed to collide in odd partial waves, P and so on. So for fermions, our topic here, identical fermions, they can only collide in P and F waves. Yeah. Now we are talking about very, very low temperatures here, sub-microkelvin, which means the velocity of our atoms is really, really low. And we need to get somehow P wave. So L needs to be 1. Mass we can't tune, that's given to us. So the only thing we can tune is the collisional parameter, the distance between the 2 atoms. So we need to crank this distance up to get a P wave collision. However, if the velocity is really, really low, we must make B extremely large, much larger than the reach of the molecular potential between the 2 colliding atoms. That means they don't collide. There's no interaction between them anymore. So that means for identical fermions, yeah, I don't, if P wave freezes out, S wave is forbidden. That's it. There are no collisions. They're like ghosts. They avoid each other. It's Pauli exclusion. So yeah, that's a problem. And for evaporative cooling, what people do is they just mix 2 different types of fermions. So say some atoms you prepare in the Mi equals minus 9.5 ground state, and others you prepare in the Mi equals plus 9.5 ground state. And then these 2 different species can collide, and that's driving evaporative cooling to a Fermi gas. So at T equals 0, both gas, all atoms occupy the ground state of the trap, whereas fermions at T equals 0, they just pile up 1 by 1 in the lowest lying states. Yeah, Pauli exclusion, no 2 identical fermions can be in the same state, up to the Fermi energy. Now we want to see it, a BEC, yeah, you can see beautifully in this bimodality and asymmetry and degenerate Fermi gas, blob. Yeah. Do you see that this is a degenerate Fermi gas? Not really, yeah? But a computer can see it. So if we analyze this here very carefully, so I integrate this absorption image up in a circle that gives me these blue marked data points. It's the radial distribution of my cloud. And then I fit a Gaussian. That's a dashed line here. And you see it doesn't quite fit. At the tip I have a little bit less population than usual. This is just here for Boltzmann distribution or so, I would be able to stuff more atoms into one state, so get a bigger density. But here in the momentum distribution, I just don't get more atoms in one. And yeah, if I then fit the correct theory of Fermi direct distribution, then it fits our data very nicely. And from that I can extract that this cloud has T over Tf. Tf is a Fermi, the temperature corresponding to the Fermi energy is 0.2. And we can also make 0.1 if we work hard. Good, that ends this first chapter of my talk, how to make a quantum gas. Done. Questions on this? No?
Just curious also that for fermions, the sympathetic cooling was other than the typical times and number of atoms.
Yes, so typically, while the gas is really purely thermal, you can perform the evaporation pretty much as fast as with bosons, so a few seconds. And then at the very end, you only have collisions between the atoms high up here, and it's actually very difficult for the atoms to find a position here, if there's a hole here, to find it. So at the very end, we typically go much slower, like it depends on your vacuum and lifetime of the dipole trap, but it can take 10 seconds or so to get a really nice cold gas. You must make a compromise, yeah? Speed of the experiment and degeneracy you want to reach. So in Junji's experiment, I think for Fermi clock it was 4.7 seconds of evaporation, if I remember correctly. Yeah, a few seconds.
And the number of atoms that you get then?
In this clock it was 10,000 atoms or so. It was very small, but we made more, like 100,000 or so. Yes?
When you have this Fermi condensation, it's possible to get lower rate temperature to Fermi temperature, let's say below 0.1.
Yes.
By the toner, let's say, or
Yeah. Other tricks, exactly. Yeah. You need to increase the interaction between the fermions. That's a way. Use a Feshbach resonance. Go to lithium-6 or something like this, where you have a beautiful Feshbach resonance between these two spin states that you mix. You can crank up the elastic collision rate enormously without introducing new loss, and then you can get to T over Tf of 0.05. And then afterwards, you have to get something like entropy distillation or something like this. Look at Marcus Greiner's quantum gas microscope experiments with fermions, where he has this 2D plane of fermions on a lattice, and he wants to see Néel order. So what he did, he put in this 2D plane a little dimple, just 10 by 10 lattice sites, where he pulled the energy of the whole lattice down. And that it's a little bit like one-step evaporation. So in the middle, you have a higher occupancy than outside. Or you can also say outside, you have lots of empty lattice sites on top of the filled ones. So if you have a lot of entropy in the system, it's a metal. You can dump all your entropy into those degrees of freedom. And in the middle, you get a nice mod insulator and see Néel order. And there's Pomerancho cooling or other methods as well. Yoshiro Takahashi uses this to see plaquette SU4 correlations. Okay, so good. Now we want to, we need to keep our atoms apart. In a BEC, the atoms are quite dense. You saw the mean field repulsion between them. That's clearly not good for precision measurements. So let's keep these atoms apart, and also at the same time we will tightly confine them, which is nice to have to suppress Doppler shifts. So this means we make a mod insulator, an optical lattice. So how do we create this? It's like an egg carton in which we place the atoms one by one, just like eggs are sitting in an egg carton one by one. How do we make this optical dipole trap in this lattice shape? We just retroreflect a linearly polarized laser beam, and then the optical dipole potential follows the intensity of the standing wave. It goes up and down in a sinusoidal pattern. And you can do this with two laser beams, then you get, they have, of course, radially, they look like Gaussians, so the atoms are also pulled radially to the middle of the laser beam, but quite weakly, whereas in the standing waves, they are very strongly confined, so you cut your sample into lots of little pancakes. In a 2D lattice, with two of these pairs of laser beams, you can cut your sample into 1D tubes, and if you apply 3 retroreflected laser beams, then you get a lattice in all 3 dimensions, yeah? Just individual lattice sites. Good. So here are our atoms in an optical lattice. Each lattice site you can consider a little bit like an harmonic oscillator. So you have here, this is the ground state of the harmonic oscillator and excited states of the harmonic oscillator. Of course, it's a sine wave, not a harmonic potential. Here, up here, the analogy breaks down, and these states here, they smear out, they form a band across the whole system. Yeah. And by the way, this is of course very analogous to a solid. Yeah. here we have atoms in a periodic potential. In a solid you have electrons in the periodic potential made by the ion cores. And if you remember from your solid state physics, you get band structures and all this kind of thing. We get this too here in the optical lattice. So we can actually use these atoms in optical lattices to simulate the physics of electrons in solid state. And this is a huge research area in its own right. But now we are just interested in preparing individual atoms in the ground state of these wells in a 3D lattice. And I'll first tell you what happens if we just load a Bose-Einstein condensate into a lattice, into just one simple lattice. Then this BEC that can still tunnel nicely from lattice side to lattice side. So you have like in each lattice side you have a tiny little BEC with a well-defined phase, and since they tunnel, all these phases are synchronized with each other. Now if I suddenly release the atoms from the lattice, then all these little BECs expand and become, each one of them becomes one big blob, and they all overlap with each other and give you rise to an interference pattern. It's exactly the same as if you would shine a plane wave laser beam onto a grating. It gives you this grating diffraction here, yeah? And you can read off, this is related to the lattice spacing here, this is related to the photons of the lattice, and I could tell you a lot more about this, but no time now. So now, another thing which we need to understand is that to making a 3D lattice, I need to cross these various laser beams, and one pair of laser beams makes a nice potential along their axis, which looks like this. But as soon as I cross the other pair of laser beams, it contributes a confinement in this direction, and it bends this whole lattice down a little bit, yeah? So you get not only the fast modulation here, but also a slowly changing envelope, a harmonic potential, which is slowly varying, or Gaussian first, but we only consider the harmonic part in the middle. Okay, now imagine we have atoms in the system, and we consider these atoms to be very cold, microkelvin or so. They for sure will not reach the first excited band, which is tens of kilohertz, so microkelvin or more above the first band. And we have just atoms sitting in these lattice wells. We can have empty wells, wells with one atom, or perhaps wells with two atoms. And you see there's something special happening if you have two atoms. They repulse each other. They have positive scattering length, so the energy of these two atoms is higher. Now, what kind of phenomena happen here? Atoms can hop from side to side by tunneling. And there's a tunnel or hopping matrix element J associated to that. That's kind of the kinetic energy which you have in your system. And then these atoms, they can repulse each other. Gives rise to this mean field shift here, U. And if I write down the Hamiltonian, I just need to include these terms here. So here's the full Hubbard Hamiltonian describing the system. So what do I see here? This is in second quantization. This AJ destroys an atom sitting on side J, which is here. This AI dagger, where I is just a neighboring side index of J, creates an atom here. Yeah? So this term is describing hopping between two neighboring sides. And I need to make the sum over all possible neighboring sides here, and then I have a prefactor which is just minus the hopping matrix element. Okay, that's describing the motion in the lattice. So that's kinetic energy here, tunneling. And then second, I have mean field energy. So this is, of course, density dependent. Here, this is the number operator on your lattice side. So n times n minus 1. So if you have 0 atoms, obviously it's nothing. If it's one atom, here you get 1 minus 1, it's also nothing. If you have two atoms, I have 2 times 1. All in all, it's 2. But here's a factor 1/2, I just get the energy U. And I have 3 atoms, I have here 3 times 2. And where is this coming from? This operator n times 1, it's just counting the number of possible interactions. If you have 3 atoms, there are 3 different ways of them to interact, so you get more interaction energy here. And then we have the external potential. Good. Now I want to show you how we can load a BEC into this lattice in a nice way to distribute the atoms one by one over the lattice sides. And that's done by the superfluid to mod insulator transition, for which we need to understand what happens if we crank up the lattice height. So here for a shallow lattice, the wave function on each side is quite spread out. We have the barrier between two lattice sides is tiny, so we have big tunneling, easy tunneling between lattice sides. On the other hand, because the harmonic oscillator ground-state wave function, so to say, is large, I mean, there's little interaction between these two atoms. Now, if I crank up the lattice, it's the opposite regime. I have a huge barrier between two neighboring lattice sides. There's barely any tunneling anymore. J goes really down. On the other hand, U gets big because you squish these two atoms on top of each other. They see each other and repulse each other strongly. So you go here from a regime where you have lots of kinetic energy and very little interaction energy, which is called the weakly interacting regime, which is kind of the trivial regime, the easy to describe one, into the strongly interacting regime where the interaction energy U vastly is bigger than the kinetic energy described by this tunnel matrix element J. So we have here a phase transition between two different regimes. So we can get strong interactions even for low densities because the lattice helps to squish these atoms on top of each other. And strong interactions, by the way, are always leading to interesting physics. So now what happens if we load a BEC into a lattice? We start with this BEC in the optical dipole trap, this harmonic trap, and we crank up the lattice. And then we have this competition between the kinetic energy and the interaction energy playing out, and this competition leads to a phase transition. It's a zero temperature phase transition, quantum phase transition. Now to understand what's going on, we simplify. No external trap. Start with homogeneous BEC with a linear density which is just one atom per lattice spacing A. So in the weakly interacting regime, I just have a superfluid, just a smeared out BEC, perhaps a little bit in density modulation, but that's it. Now I crank up the lattice, and the atoms then distribute one by one over these lattice sides. Why do they do this? Imagine they wouldn't. Imagine I had a flaw here. Imagine one of these atoms hops to the neighboring side. I need to pay for that. This costs me energy, U. This is disfavored. Okay? So if I crank it up very, very slowly, I go from this ground state to that ground state, avoiding this excited state. It's because it's gapped. I can do this. And so if I will be able to do this, just load the atoms into this state. If I have twice as much density, I will obtain such a state. It's also gapped. If I move one atom to the side, again I have to expend energy, because here I suddenly have 3 U. Of course, here I save 1 U because I don't have 2 anymore, but all in all I still spend 1 U. So this is favored. And if I have something in between, I get, say, a mod insulator on bottom, 1 atom per side, plus a superfluid on top. Okay, if I look at the number statistics, so if I am in the BEC phase, the atoms wildly tunnel from side to side, and actually at each lattice side I have a Poissonian distribution, a superposition state of different number states. And if I take a snapshot, sometimes I find no atom on a side, sometimes 1, sometimes 3, and so on, Poissonian distributed. If I prepare a mod insulator and I just choose the right density, then I have exactly 1 atom per lattice side. And this is beautiful. This is what we want to build a nice clock. The atoms are nicely separated from each other. And how was this seen the first time in experiments? So you remember these time-of-flight absorption images, diffraction from a lattice. Now we do this with a 3D lattice, which gives rise to this diffraction pattern in 3D space, which we look at from the side. So if we have a superfluid, yes, then I get now these diffraction peaks. But if I crank up the lattice, something strange happens, and these diffraction peaks go away, and I just receive only 1 blob. Why is this? Okay, this you understand. A superfluid is just an grating diffraction. A mott insulator, these atoms are nicely separated from each other. They don't share a common phase. Each atom sits in the harmonic oscillator ground state of the lattice site. Now from Heisenberg, you know, if delta x is small, like in the harmonic oscillator, delta p will be large. So if I switch this lattice off, all of these wave functions will dramatically expand. And they're incoherent with each other. They just add up. So I just get a blob. Yeah? And now, yeah, that shows you that you get a transition from a superfluid to possibly a mott insulator, or it might mean that you just heated the crap out of your sample and it's all decoherent. But to prove that it's really nice, you just go back. Here, this is with strontium. BEC, mott insulator, and then we ramp the lattice back down again, and we get back the BEC. So that shows that this whole process is adiabatic and that we really had a phase transition going on. And there's another beautiful way of seeing this physics with single atom microscopes. So imagine I have these atoms here in the lattice. Now I just shine my mott laser beams on them, and these atoms will fluoresce, and and I can collect this fluorescence. And if I have a microscope which just is good enough to resolve these lattice sites, I can see bright spots wherever I do have an atom in a lattice site. There's one tiny complication here. If I initially had 2 atoms in one lattice site, they will go away. And so what these instruments usually see is not the atom number, but the parity of the atom number. If I have parity means if I have an odd or even atom number there. If I have 2, I see dark. If I have 3, I see bright, because 2 go away and one survives, and so on. Okay, and that's how these machines are constructed. Just this is the one from Immanuel Bloch, the first one with rubidium in Munich. They make up BEC here and then load it into an optical lattice, and then they have this fancy microscope objective to record the fluorescence. And now there's one thing which I didn't explain you yet, and that is in this mott insulator we always, well, let me scroll quickly back to here. We always have this external potential here, yes? This is very important. Now in the middle I have higher density than outside. So if I look at my gas cloud, I will see higher density in the middle than in outside. And in a superfluid, it's just going to be like a roundish parabolic blob. Whereas if I have a mott insulator with high density in the middle, I might get, say, 2 atoms per site in the middle. And then here out is the density is lower, and I get perhaps 1 atom per site, and then 0, yeah? And always nicely discretized. So let's look at these results from the quantum gas microscope. Here they are. If I image a superfluid has Poissonian atom number statistics on each lattice site, yeah? So it's random. It's really a superposition state of all possible atom numbers, and if I take a snapshot, the wave function collapses to a specific atom number, and I will record that, yeah? And that is why it's pretty random what I see here. I also only see odd or even, so it makes it look even more random. Now if I make a mott insulator, look how clean that suddenly is. Yeah? On each and every lattice site in the middle, they have exactly 1 atom. And now they put more atom in the system, which means they increase the density in the center. Initially that just makes this mott insulator grow bigger, but at some point they exceed, they have too many atoms in their system, and it's not favorable for the atoms to pile up out here on the hill of this harmonic external confinement, and they rather roll in and form a mott insulator with 2 atoms per site in the middle. But 2 atoms per site looks dark, yeah, because of parity projection. So that gives you this ring of a n equals 1 mott shell and an n equals 2 in the middle. And then they increase the atom number even more till they got n equals 3, n equals 2, n equals 1. Okay, so that is what I wanted to tell you about the mott insulator. Now I have 1 slide left, putting all of this together and building a clock. Now I'm not going to explain you how a clock works. You will do this. But I'll briefly show you some results of the Chun-Yi 3D optical lattice clock experiment. So they prepare a degenerate Fermi gas of strontium exactly like I described it to you, with a spin mixture of atoms in the +9/2 and the -9/2 ground state. And that is just a snapshot of one plane of their 3D optical lattice. And of course, after they load, it looks somewhat like this. You can't control which spin is on each lattice side. Now, they drive this millihertz clock transition. There are interactions between atoms. If they happen to have two atoms on one side, they interact with each other, totally shifting the clock transition away. So those atoms will just not be influenced. They tune the clock transition just to say the +9/2 state, not the -9/2 state. It's split a little bit by magnetic field. So they excite only singly occupied sites and only +9/2 states. They go up here, okay? And then all the other atoms where we have doubly occupied sites or the -9/2 states, they just blow away with the blue laser beam, you know, the strong laser transition. So now you have a very clean sample. And then they run the clock interrogation, which runs a spectroscopy, which will be explained later. So you place the atoms in a superposition by an pi/2 pulse on this transition. Then they wait some time, and then they make another pi/2 pulse, and then the atoms come out back either in the ground state or in the excited state. And where they come out, that how many are in the upper state, how many are in the lower state, and so on. This gives you information about the relative frequency between your clock laser and the transition frequency of your atom at that location in the lattice. And then they have a high-resolution microscope objective with which they analyze their sample. It's not single-atom resolving, but still high-resolution. And they first make an image of all the atoms in the ground state. Then they optically pump the atoms in the excited state down and make an image of those atoms. And then they normalize these two images and get the excitation fraction. Now I'll show you just one experiment. Here they try to make the sample as homogeneous as possible. All the transition frequencies of all these atoms are quite close to each other. Now they, by purpose, apply a magnetic field gradient across their sample to tune the transition frequency at one edge differently from the other edge. And then you can see here alternatingly how atoms react to this. Yeah, some in stripes they go up and down, up and down. I would have to describe Ramsey spectroscopy sequence for you to explain this total, but you will do it anyway. So just take it from me that this here gives them information about the transition frequency at these different locations in the trap. And their coherence time here is 15 seconds, and they have a precision of 2 × 10⁻⁹, which is pretty high. Good. That's it. So I told you why quantum gases might be interesting for some precision measurement applications, also for atom interferometry, of course, because a BEC, when it expands slower than a normal thermal cloud and so on. Showed you why it's difficult to reach BEC with just laser cooling, and that evaporative cooling is usually the method of choice to get a BEC. For that you need magnetic or optical dipole traps. There are some difficulties in Fermi gases. And then I showed you how to make a mod insulator and use that to make a clock. Yeah.